Hi, we're going to be taking a quick look at light. There's going to be a couple videos in here that I'm going to need you to stop this video and go watch those. So just be warned, those are coming up. So what is light? Well, light is photons. They travel in waves out of the sun. And basically, to get that light, to get those photons released, you have to have nuclear fusion. The sun's energy is actually nuclear fusions. We're taking the smaller elements, hydrogen, and fusing it into helium and fusing it all the way up to about carbon. After that, to get the heavier elements that you'll learn about in physical science, you're going to have a star explode to get enough pressure to create those atoms. So what happens is, think about it this way. If I have the protons in the nucleus and you're getting them squished together, you're literally also forcing the electrons to come together, and they can jump shells. And as they jump from one shell to another, they release energy in the form of photons, what we perceive as light. There's different forms of energy also coming out, but electrons' energies are larger here than here. So if it comes from here to there, it has to release some of its energy that it had up here to come down to this level as it gets squeezed together. And that extra energy is actually released as a photon. And so the path of that photon isn't a straight line from the core where all the pressure is, where the nuclear fusion is happening. It takes this very random, as it bumps into other things, path all the way out until eventually it escapes out to the edge of the sun and goes off in all directions. Because remember, our light from our sun is traveling in every direction that there is. So we have photons, we have neutrinos, all of these things are being released. As we look at it, you can actually see the core. We have the core of the sun, and then there's different layers. And when we talk more about the sun, we'll actually start naming those layers. But for now, just know that the sun, like the earth, is comprised of layers. The core is the center where fusion is happening. So what does the sun release? Well, it releases gamma rays, X-rays, ultraviolet, that is UV rays, the ones we want to block from getting us a nice little sunburn. Visible light, which is just a small part of the spectrum, the electromagnetic spectrum. Infrared, microwaves, those include what we use for our cell phones, and radio waves, which also include TV signals. So light is the only thing you see. Well, actually, you're seeing it being reflected back off of an object, because objects absorb different colors of the spectrum, and the one they don't absorb, they reflect back, which is why we get all those beautiful colors. All visible objects either emit or reflect light. The sun emits light. A light bulb emits light. The moon reflects light. The earth technically would reflect light if you're from outer space, but on here, when we're on the surface, we can emit some light. Fire emits light. But in 1905, Einstein published a theory explaining the photoelectric effect. According to this theory, light consists of particles called photons, massless bundles of concentrated electromagnetic energy. And when we're looking at that energy that's being released, here is that whole electromagnetic spectrum. Pulsars we can see them through X-rays. The sun, we can see invisible light. The stars, we can see invisible light. But we can also use radio waves. We have radio telescopes. You've learned about those. And active galaxies a lot of times are really loud. They are emitting a lot of radio waves. But this part that we see is just a teeny tiny portion, that Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. Gamma rays have very short wavelengths, where radio waves have very long wavelengths. And that's the distinction between the different parts of the electromagnetic spectrum, is the length of the wave from crest to crest, the top to the top, or from trough to trough, the bottom to the bottom. So we go from gamma rays to X-rays to ultraviolet to visible light, infrared, and radio waves. This is where I would like you to stop and watch this video clip. And this is going to go on just talking about a little bit of the sun. And it's 1 minute 36 seconds. Then when you're done, please come back. Okay, hopefully you took a moment and watched that video. Again, here's just another rendition of the electromagnetic spectrum. and the little tiny bit we see is right there. Newton was the one that discovered that light behaves like a wave. He took a lot of time with a hole in his curtain, and he split light coming through that little hole with a prism, and he discovered that you could break light into different colors. But when you put them to the other side, you could mix them back to white, but you couldn't break those colors down smaller than that. And he also went in to discover that each gas emits different lines, and this is an emission spectrum. So there's this whole spectrum of the colors, the Roy G. Biv, and each gas as it burns actually emits a different color signature. And that's how we can differentiate one gas from another. It's how we can tell what gas is comprised in a star. This 3.5-minute video clip is all about Newton and his discovery of that. So if you could again stop, watch that video, and then watch this next one, which is less than a minute long. Those are going to be talking about finding the electromagnetic spectrum, the portion of it that is visible light. Please stop, go watch that, come back. Okay, waves. If you've ever had the opportunity to be in the ocean and you go just far enough out where the wave on the bottom isn't actually running in, you will actually really not move that far. You'll actually just bounce up and down, you'll ride with wave. The energy is actually transmitted through the water. That's that rise and fall. But the actual water isn't transported until the bottom of the wave hits the shore, the bottom of the ocean, and it forces the wave up, and only then will you start to have water actually moving forward. So if you were out, say here, and you were just bobbing up and down, you would just ride the wave. So a wavelength is from, as I said this before, from crest to crest, the top of the wave, or from trough to trough. So if I look at it here, here's one wavelength from this crest to this crest. Amplitude is how far above from the center it goes. The trough is the bottom. So a wavelength could also go from trough to trough, or from crest to crest. Scientists now agree that light has a dual nature. It's part particle and part wave. So what happens is you've got the one wave going this way, and then you've got another one going this way, and the two together perpetuate the motion and keep it going through space, because remember, in space there's no medium for that wave to travel on. So with that, like sound, there's no sound in space. When you watch Star Wars, so when you watch Star Wars or Star Trek, Star Wars more, and you hear all those firing shots, that's not actually, you would hear it at all. There would be no sound. Okay, so there's no sound in space. There's no medium for sound waves to travel on, and they need a medium to travel on. Light waves don't need that. So the speed of light in a vacuum is a universal constant. The light could travel around the Earth. It would make 7.5 trips every second. It takes 8 minutes for light to reach the sun, from the sun to get to the Earth, and 4 years from the next nearest star, Alpha Centauri. So think about that. In 8 minutes, light travels 93 million miles to reach us from the sun. That's fast. The distance light travels in 1 year is actually called a light year. So the funny thing is, a light year is a distance. It's not a time. So in other words, in a vacuum, the speed of light is a constant 300,000 kilometers per second. That's how far it travels every second, hence the number of times around the Earth in 1 second. We call that, the speed of light is called c. And if you know Einstein's cosmological, all that constant fun stuff, E equals mc squared. E is energy, m is mass, and c is the speed of light. And so interestingly enough, that means that we can speed up and slow down time if we approach the speed of light. Technically, because if you had twins, one was when we used to have the space shuttle going up, that was traveling so much faster, they would come back technically microseconds younger than their twin that remained on Earth. Because as you go faster, time slows down, because it's a proportional relationship. Interestingly enough, there is a way that we can slow down light, and it's called glass. So as light travels in, it passes and vibrates the next energy all the way through. But as it goes through, remember, it bends light just a little bit, and it slows down. And then the interesting thing is, it excites the next one, and then that one's energized, and then that goes and hits the next one, and then that's energized, and then it exits the other side, and then it kind of burps it out, and it's now traveling again at the speed of light. Light is the only thing that can travel at the speed of light. We can get really, really, really close, but we can't get that last fraction of a percent to get past that 99.9999 whatever. We just can't do it. If you were born going the speed of light, you could go the speed of light, but if you ever slowed down, you couldn't attain it again. And that's the crazy thing about light. There are some interesting physics rules that go into apply that don't really make as much sense from our perception, but we don't have a perception of traveling at 300,000 kilometers per second. What you're seeing here is reflected light. Nothing in this picture that is the Earth or the Moon is anything but reflected, but the stars around it, that's emitted light. This is a moonrise, but is it? No, that's an Earthrise. We're on the moon at this point from this vantage point, looking back at that marble, which is our planet that we live on. This little floating ball of blue oceans and land that keeps us going. That's a pretty cool thing. So if you're on the moon, here's a time lapse of a Earthrise. So if you're on the moon, you get to see an Earthrise. You could also see a sunrise. We see the moon rise and set every night on Earth. We don't think about it the other way, but it does happen. But this is reflected light. The moon does not emit any light. It only reflects light. The Doppler effect. I'm going to play this one because I want to make sure you get this. Here we go. Maybe. Let's try it again.
Another common occurrence that depends on the frequency of sound waves is one that we have all experienced. It happens whenever there is motion between the source of a sound and its receiver. The pitch of the sound is higher as it approaches us, or we approach it, and lower as it or we move away. This is called the Doppler effect. When there is no movement between the source of a sound and its receiver, sound waves are sent out equally in all directions. When there is motion, sound waves either pile up or spread out, depending on the direction of the motion. When the motion is in the direction of the sound waves, they are pushed together, producing a sound with a shorter wavelength and a higher pitch and frequency. When the motion is away from the sound waves, they are more spread out, producing a sound with a longer wavelength and a lower pitch and frequency.
Okay, so that's that ear you get when you hear a car approaching. That high pitch as it's coming towards you because it's being compressed, and then as it goes past you, he's actually or he or she, whoever's driving, is pulling away from their sound waves behind them, kind of like a duck in a pond. If you notice the ripples going out as they swim forward, their ripples get bunched together, but behind them they're elongated. And that is seen in both sound and light because they're both waves. So the car traveling towards you is compressed, high-pitched. As it pulls away from you, it's actually pulling away from its wavelength, creating a lower pitch because it's farther distance from crest to crest or trough to trough. And here's that duck. Compressed, high-pitched, pulling away from it, lower pitch. The same thing happens with a sonic boom. The interesting thing is, in light, it also compresses. But and from that electromagnetic spectrum way up here, remember, if we have a light source that's coming towards us, it compresses its waves and it shifts to the blue. If it's going away from us, they're pulling away from there and their wavelength gets longer, so the visible light actually becomes red. So Doppler effect works with sound, high pitch and low pitch, but it also works with light. And that means if it's coming towards us, it's a blue shifted object, and if it's going away from us, it's a red shifted object. The other thing you want to think about too is don't be confused with hot and cold and all that, because coming towards us is blue. But we can see this. If you have a flame, and this is why I was trying to get to the point that colder is determined by temperature, right? It means how hot something is determined how hot or cold it is. But if you actually look at a flame, a blue flame is hotter than a red or an orange flame. So we have all these different color things we can think about. But in a color spectrum, if I'm looking at heat, blue is hot, red is cooler than hot, green is kind of warm. So, but we also have a shift that's occurring here. So the ones that are shifted towards the red could be cooler, but they're also going away from us. And the ones that are shifted towards the blue could be hotter, but they're also coming towards us because it's a blue shift. So red shift, blue shift, good test question. I can tell you that right now. You need to understand the Doppler effect. High pitch sound, short wavelengths. Low pitch sound, longer wavelengths. If I'm talking light, a blue shift means it's coming towards us. A red shift means it's going away from us. Here is a quick review on that. It's 1.5 minutes long. You should go and watch that when you're done with these notes. And then you need to go down in here and explain to me what is the difference between red shift and blue shift. Okay, hopefully you're back and you've watched that video and answered that question. And now we're going to get into absolute and apparent magnitude. There is a difference. Absolute magnitude is how much light is actually given off by a star. That is how intensely it is. If I was the same distance from two different stars and one was brighter and one was dimmer and it was the same distance away, I would know its absolute magnitude. But its apparent magnitude is different. Its apparent magnitude is how bright the star appears to be due to how close or far away it is from us. So we can look at a constellation of stars, and one constellation of stars, honestly, may be hundreds of millions of miles apart. But if one really, really far away is super bright and the ones closer to us are dimmer, they all appear to have the same apparent magnitude. So, two astronomers discovered this relationship between the absolute magnitude, that is real brightness of a star, and its surface temperature. And then they plotted that data on a graph. And they drives me crazy because they plotted it backwards from how I would do it, but that's just me. Just know that it's, read the numbers and you'll be fine. And the name was Egnar Hertzsprung and Henry Russell. One was Denmark, from Denmark, and the other was from the US. And they named it the Hertzsprung-Russell diagram, and that is this diagram right here. I'm going to make it just a little bit smaller. You can enlarge it on your own, but I want to make sure we can see the whole thing. And what's interesting in the life of a star, most of the time we're in this main sequence. This is the main sequence. This is where most of the stars spend the bulk of their life. Depending on how much mass they have, they can become a giant star. They can become a supergiant star. And that's as they die, they expand. And then as they expand, they actually implode back in and shrink down, and they can become white dwarfs. Now, if you look at this, you'll also notice in here that there is a color variation, and that has to do with temperature. And this is where it drives me nuts, because you'll notice down here is temperature. It decreases in temperature to the right, and it increases in temperature to the left. And for me, that just doesn't make sense, but okay, we'll go with it. So here in the red, you're talking about 3,000 Kelvin, where over here you're talking 30,000 plus Kelvin. And remember, surface temperature in Kelvin, that's how I know that's Kelvin. So if we look for our sun, we could go in and find it, and we'll enlarge this in a second, but I can tell you right now it's right here. And if I follow that straight down, because that would be a good test question, it would be a G-type star, and it's just over about 6,000 degrees in temperature. Now, this on the bottom is temperature. Up here, this is luminosity. And the higher up you go is the brighter, and the farther down you go is dimmer. So high is bright, low is dim. Far to the left is hot, far to the right is cooler. So we're not a very hot star compared to that, and we're kind of almost just we compare it, we're Earth-centric, right? Because this is what we're used to. So we say that comparing every other star to ours, our star is 1. If you're dimmer than we are, you're less than 1. If you're brighter than we are, you're more than 1. So a lot of stars are brighter than we are, and they are huge. And when we get into star size, you'll see just how big some stars are compared to what we know of as a pretty, decent sized star. It takes care of us, it keeps us alive, gives us the energy to heat and cold, and of course, snow, all that good stuff. Because if you're in the year that I recorded this, we just had 6 inches of snow in the middle of October. So as we look at this, I would also go over here, and then I'd say that the luminosity of our sun is 1. Our temperature is just over 6,000 degrees Kelvin. But let's say I want to look at, let's make this just a little bit larger so you can maybe see this a little better. Betelgeuse right here. Big main sequence star, but it's definitely shifted to the blue. If I go all the way down, it's about a B class star. And if I look at that, that's somewhere between 10,000 and 30,000. Shifted probably a little closer to the 30. So let's say it's 22,000 degrees Kelvin roughly. So I would never ask you specific. I would say generally what's the closest number, and that's what you come up with. So it's a bright star because it's higher up, and it's a hot star because it's further to the left. And if I look at Betelgeuse, I go over, its magnitude is almost 10 to the fourth brighter than our star. Again, I would just ask you roughly, is it between 10 to the third or 10 to the fourth? And remember, we just tack on some zeros to figure that out. So they discovered that the stars are grouped by type during their lifetimes and move from one place to another on the graph. As our sun ages, it moves to a giant star and then a white dwarf. That's our life cycle of our sun. We're not going to necessarily watch Amazing Sun, but it is a sun video that we will be watching in class on the next day. So when you have watched the videos on here, obviously you're now done with mine because you're seeing this part, you are going to answer that question on Doppler and then hit submit. Ask questions as always.